Good afternoon, everybody. It is a pleasure to introduce today's speaker, Professor Dovi Poznanski. Dovi is professor at Tel Aviv University and visiting professor at Stanford currently. Dovi got his PhD at Tel Aviv in 2007 and then spent 4 years in Berkeley as a postdoc. And you have one guest with whom. And one of those years was spent as an Einstein Fellow. He also got a couple other honors and fellowships as well. He returned to Tel Aviv in 2011, first as a lecturer and then as faculty, been there since. So Dovi is one of the pioneers of astroinformatics, one of the first people who start using machine learning for practical purposes. And today he'll tell us about present and maybe future.
I'll try very hard not to make predictions, especially about the future. But thanks, George, for the invitation and for the introduction. It's a pleasure. I spent a lot of time thinking about what I wanted to talk about here today because I thought it'd be very odd to talk about AI or machine learning, and I will use those two terms interchangeably because I think they're both about as meaningless today as they can be, without talking about them in context, some societal context even, but I promise to make it tiny and mostly talk about science. And I'll argue that there have been a few evolutions or revolutions going on. And when I talk about observational astronomy, it's really shorthand for things I was personally involved in some ways. Obviously, I'm not claiming I can cover everything or anything. This is sort of the question I want to address today from various angles. When we're talking about machine learning or AI, are we talking about toys, or are we talking about useful tools, or perhaps the greatest threat to humanity, or as a great thinker recently said, we're smart enough to invent AI, but too stupid to know if we did the right thing. Briefly, I think they were toys, but they've become necessary in many things we're doing and quite useful. I wouldn't call them a greatest threat to humanity, but a significant threat to society, I think, is a fair assessment. But first, this is a quote from David Arnett. Dave Arnett, more than 10 years ago when he got a prize at the AAS, and I remember him saying it, and I wrote it down because I really liked it. And he said, we have to work really hard in order to get computers to do what we want them to do, rather than what we want them to do. And which is beautiful coming from one of the pioneers of supernova computational astrophysics and simulating things in the computer. And I think today it's a lot less true. Computers understand us much better. And this is, I think, a big deal. And I think it's something worth acknowledging. LLMs, large language models, are problematic, and I will touch on that. But they understand natural language, and I think that's quite incredible. In fact, there's been progress in many fields just in the past few years, and it's accelerating. So there's progress in the past few weeks on many of those things, from vision and natural language and translation and multimodality, so being able to deal with images, text, and voice, both as input and outputs. Coding, of course, and also reasoning, actually thinking on problems, from Go and chess in games and Jeopardy to actual problem solving. But if we go back 15, 16 years ago, when we were starting the Palomar transient factory with many people from Caltech, probably some in the room, machine learning was, for most people, something that's either sort of in the sci-fi world or perhaps toys. But for us, it was already part of production. I mean, this is a plot from, actually, I don't remember which of those papers. I think from the Bloom paper or the Rao paper. But we were having about 10 to the 6 candidate supernovae per night in that survey, of which only one was, on average, an interesting object. So we were swamped by things, and we had to use some tools, and we weren't the first to do it. Actually, Stephen Bailey wrote the first paper on how you could separate the true transients from the bogus. And we did that as part of the pipeline back in 2008. But this was 15 years ago. Today, you have these complicated machineries. This is just an example, but this is an example of, I won't even try to go into the details of what they do here. But these brokers that are now basically trying to serve the data from these big surveys that are finding many, many transients, and it's impossible to sift through all that without some help from machines. And another example from this group, again, with many people from Caltech, where robots are actually making decisions and starting follow-up. You can see here that this was a machine learning model. Where's I pressed the wrong button, I think. There it is. A machine learning model that autonomously triggered on a target the follow-up spectroscopy. So the whole thing of using machine learning and AI in the field of transients started much earlier than other fields. And the obvious question is why? And the obvious answer is because we have no choice. We just had to use something, and we couldn't do it in any other way that we knew. The other important point is that the cost of error was relatively small. This is not part of the actual analysis of the data and trying to get to the physics. It's just finding the objects. If some of them are not what we wanted, we missed some, or we observed a few that we didn't care that much about, the cost was relatively small. But then again, the main thing was the fact that we had no choice. The question is, okay, so that's been happening. Where is that going next? Where is the field of AI and transients going? And I think it's worth talking in the context of this. So this was a competition, data challenge that happened in the last couple of years in preparation for Rubin and LSST, thinking we're going to get all these light curves of transients. And we need help from the machine learning community on how we can sort through that and find the ones we care about, etc. And you can see a lot of participation from 1,000 teams, over 1,000 teams participated in that challenge. Before I get to the result, I want to briefly talk about the problem, which is classification of transients. So you get these objects, you want to know what they are. There's really two different problems. One is the early classification, one is the late classification, and they're different problems. In the early ones, you just observed, you got 1 or 2 points on the target. You know perhaps something about the galaxy it exploded in or appeared in or something like that, but that's it. You don't have a lot of information on the object. So it's sort of this sort of empty diagram here where you only have the beginning versus also relevant and interesting problem. You've observed for a couple of years, you have a lot of light curves, and you want to classify them into various bins of various types and find which is what. Now that I've split them into two problems, I can treat them again together and say that neither of them is really, I think, an AI problem. And I think they're both data problems. And what I mean by that is that the difficulty is not so much that we need some fancy algorithms, but we need to understand the problem better. Our data tend to be sparse. We don't have many points on those light curves. They're noisy because we're looking for the faintest things we can find. Our priors about what they are tend to be relatively weak because we don't know well enough the luminosity functions of the various transients. When do they explode? Where do they explode? How many of them we should expect? So what are their cosmic rates? We have some constraints on those things, but they're difficult to measure and therefore difficult to propagate to our models. And even worse, we have bias priors. And by that, I mean, we got spectra and we have data for many transients, but they're anything but representative. We got spectra for the things typically we were interested in, that were brighter or easier to watch or weirder and not the regular things that we've seen so many of that we don't want to see more. And so trying to get from a set for which we have spectroscopy and train a machine to be able to apply it for other objects is challenging. And therefore, it's not really surprising, going back to the data challenge, that out of those thousands of machine learning experts, the winner was Carl Boone, very knowledgeable in machine learning. I don't want to say anything bad about Kyle, but he's a supernova expert. And quoting from his submission, what he did was augmented the training set by degrading the light curves in the training set to match the properties of the test set. This is a step that no machine learning person would ever do, because by definition, the training set is representative. It's a training set. We train on something representative. But he understood that that was just not the case in real astrophysics, and you had to do something to account for that. Next step is using Gaussian processes to predict the light curve. So that's a good way to interpolate and deal with the sparsity I mentioned earlier. Measured 200 features on the GPs and on the actual light curve. So he used his knowledge of the field to find and measure on those light curves the things that will be useful to eventually classify. And then he used a relatively simple model in the sense that it's not some fancy deep learning model or anything like that, and worked better than anyone else. So if I need to summarize this short piece about transients, I would say this. Transient astronomy has undergone a quiet AI evolution. It just happened. We needed it. We used it. It's fine. It's useful. We use it where we can, and we get better at doing it, and more fancy depending on what we need. And really the standard now to incorporate it everywhere. And every survey, broker, group tailor them to their interest. And I really don't think there's a lot of very interesting things happening from a methodological perspective. Domain knowledge, knowing really the field in which you operate, is the main key here. And I think a major challenge lies in building training sets and in measuring cosmic rates so that we'd have better priors moving forward. And I know there are big efforts happening here on that from ZTF. You have the bright BTS and CLU. So the CLUs is I don't need to remember, I have it written here, is the census of the local universe, and BTS is the Bright Transient Survey. Both are basically trying to take this fire hose of data from ZTF and say, if we constrain it only to the brightest or nearest, then we can be somewhat complete or as complete as we can, and then we will have a way of measuring rates and luminosity functions and things that we really need to know moving forward, and that will also teach us a lot about these objects. That was one. I want to sort of broaden the picture, move to slightly different things, and talk about this trope of astronomical haystacks. And finding needles is easy if all you need is a magnet. But how do you find the one blade of grass that's kind of different, which is what we're trying to do here. The idea is we're generating tons of data, different surveys, different wavelengths, different types of data. And the question is, how do we find anomalies? There are too many objects to look at, just too much data, and too many properties or dimensions of combinations of those properties and dimensions to actually look at everything. So how do you move forward for that? Perhaps before the how, we should answer the question of the why. Why should we care about the anomalies? Debugging is one good reason, especially when you're generating that much data. You want to make sure that you capture the errors and you don't always know where they're going to be. So this is a useful thing, even if it's not very exciting. Should probably remember that quasars were once weird stars and pulsars were weird radio sources. So we should be open to the possibility that there are things we didn't expect. But I'm not expecting to find the next quasars every time I look at a new data set. But even finding objects from a class we already know and we've already studied, and finding the weird ones in that class can be useful, because it helps us basically test our models and see if we can accommodate for those new objects. Another point I think worth mentioning is that, in a way, in astronomy, in the universe, everything is rare. Supernovae are a rare occurrence. Stars are rare. If you're in a random position in the universe, most likely you're far away from a star. So it sounds like by saying everything is rare, I'm not saying anything. But what I'm trying to say is that if your problem can be phrased as an anomaly detection problem, then you can use those tools. And I'm saying many of the things we think about and work with every day are in some sense anomalies. And so it's worth considering how those tools could be applicable and useful. And last, and this is again something that's special to astronomy, something that is rare could be common but short-lived. We only have snapshots. Things happen on short timescales could just evade us because of that and still be very interesting. Just to give two examples for the types of data sets I have in mind, and I will get back to some of them, or in a way you'll see. On one hand, you have things looking at optical spectroscopy. DESI, that came online, I think, 3 years ago. 5,000 fibers, about 50,000 spectra per night. So generating samples, the EDR, the early data release, had already a couple of million objects, but they're going to get quickly to the tens of millions. And this is just one survey. You have Sloan 5 and PFS and Foremost and more. The image here is just 1/10 of the whole pizza pie. That's the focal plane. So you see here these 500 fibers if it's 1/10. And just to give another example from the imaging side, this is from the 23rd data release of ZTF, and these are the numbers of detections. So numbers in the trillions or something. I don't know. There are too many digits. I get lost. How do you find anomalies? You can just eyeball everything. Obviously, that won't work very well with large data sets. You could feed a model, and then you look at things in parameter space and find the objects that are extreme, or perhaps the one that were not well fit by the model. And that's a good way to find anomalies. Another is to use machine learning, which is in some way the same thing. Only the model you're learning is flexible and it's phenomenological and not necessarily motivated by the physics. But essentially, you do the same thing. You fit the model that allows you to map this high-dimensional data into something that is lower dimensional and meaningful, and that's a point I'll get back to, and then find the outliers. There are many things you could call outliers. This is from a recent review. You can have groups of objects that are outlying or single points that are outlying. You can see here in the context that if you think about these as light curves, for example, these are two different types of anomalies you could find equivalent for in astrophysics, whether it's an anomalous point or an anomalous point on a light curve or an anomalous light curve. And you can really find parallels in others. The difficulty, and also I think the part of what makes it interesting, is that there are many possibilities, and there are many good algorithms, and they find things, and you change their parameters, and they'll find something else. These unsupervised tasks are ambiguous by construction, and they rely on a notion of distance or similarity. I want to be able to take two things and ask how similar they are to each other, or how close in some space. And this is also ambiguous. And obviously then the results and the quality of the result will depend on those choices. And just to be silly and to have a cat, because I don't think you can have a talk without cats. I think there's some rule about this somewhere. If you try to think which one is the outlier here between the chair, the pencil, and the cat, you might think that the cat is the outlier because the other two are made of wood, mostly. Or you can think that the pencil is the outlier because the other two have legs, which also makes sense. I would argue that the chair is the outlier because it's the only one I would consider thinning on. So I wouldn't sit on the pencil and definitely not on the cat. But all those things, ways of comparing things are valid. Now, when you have something like that, so this is an example that is often shown. These are digits, handwritten, and they're digitized. So everyone is represented in a small thumbnail with about 900 pixels, 28 by 28. So this is the dimensionality of the problem. You have 900 features, the value of every one of those pixels. You can choose an algorithm for dimensionality reduction. I'm just giving some sort of broad families or examples. For each one of them, typically, you need to decide on a metric on how you measure distances between objects. Then they have a bunch of hyperparameters. But if you start with digits and you do that and you map them to a two-dimensional space, you can see that they tend to cluster, if you did it well, so that all the 2s go in the same area and the 3s are there and the 0s are there, and some are easier or harder to separate. But how do you choose? I mean, here with the digits, we have labels. We know that this is a 2, this is a 1, and this is a 9, so we can train and use that. When we're doing anomaly detection, we're really learning with no objective function. We have, our purpose is finding outliers, but as I just said, outliers are ill-defined. There's no good definition of what is an outlier. So the only way forward is educated experimentation. We try things. And the more you know, and it goes back to a point I was making earlier with the transients, it relies a lot on domain knowledge, a lot on understanding the field in which you're operating and not just on the tools. One way I would like to emphasize and talk a bit more about is self-supervised or contrastive learning. And this is a very useful idea. And the idea is that you use some pretext task to force the algorithm to learn whatever it is you want, whether it's labels or a metric, from unlabeled, in our case, observational data. Just to give an example, the large language models that I briefly talked about earlier, one of the ways they're trained is by learning how to basically replace, fill in the blanks in text. So you take a text, remove a word, what is the word that's missing there? We don't really need the LLMs to do that. That's not what we train them. But by teaching them to do that, they learn language, which is, by the way, quite amazing. But the pretext is fill in the blanks. The result is they learn English and they learn text and how to communicate. But you don't need to go to large language models and transformers and fancy deep models. We did this back years ago with random forest, and the idea is the same. Briefly, because I'm assuming not everybody knows always what is random forest, and I don't think you really need to, but if you care, we can talk about this more later. Random forest is an algorithm, but it's funny that something from 2001 is old, but it's kind of old. The idea is to build many classification trees, and each one of those trees is trained on a subset of the data. So I don't know, galaxies, and the tree and the forest learns that if the color is greater than something, then it's an elliptical, and if it's smaller than something else, then it's star forming. And if you cut by radius and cut by whatever properties, and then you can different ones like that. And each one of those trees learns from a specific subset of the data. And then if you want to do classification, you aggregate the results from all the trees. So you take an object, you send it through all the trees. 70% of the trees said it was an elliptical galaxy, therefore it's an elliptical galaxy. With the self-supervised random forest, you begin the same thing, only you classify all your sample, 100% of it, versus 100% of a completely fake sample that you generate in a way that I won't go into right now. But you have these fakes and you have the reals, and now you train the random forest to separate between them. In the process, you've taught the algorithm what a normal object looks like, what an object in your sample looks like in order to be able to do that separation. And then you can take two objects in your sample. You can throw away the synthetic data now. You can take two objects in your sample and ask how often they land in the same leaf in every tree. If two objects are identical, in every tree, they will branch exactly the same way and end up in the same place. If they're completely different, no matter what question you ask, one will go left, the other will go right, they will never be in the same leaf. And you have everything in between. And so counting in what fraction of the trees they land in the same leaf is a measure of similarity. And a way basically to find the outliers by defining them as those that are least similar to others. We tried that the first time on the Sloan galaxy spectra. So these are optical spectra of galaxies, about 2 million of them at the time, and calculated this weirdness score, basically how score itself doesn't matter. Basically, they're ranked by how distant they are from all the other objects. So the ones that have the highest score are furthest from others. We found quite a lot of interesting things. I will just show one example because I don't want to spend more time on this specific work out of all of them, but it just shows the kind of things you can find when you don't know what you're looking for. And in this case, I'm showing just a small piece of the spectrum, and you have to have seen quite a lot of spectra of galaxies to realize that this is not a line. The line at 5,200 angstroms is not a line you should be seeing. You just don't see it in galaxies. Galaxies don't have a line at that wavelength, or at least 999,000 out of a million complete all the nines. Because we found actually a few looking more carefully, but that's pretty much the numbers. We're talking about the 1 in a million object in terms of the scale. This is nitrogen 1, so you shouldn't see it in galaxies. It's very easy to ionize. And in fact, the Furlan paper from 2012, Gary Furlan's the one who wrote Cloudy, is trying to understand how you can get that line in planetary nebulae and supernova remnants. And when I told him that we see it in galaxies, he didn't really, there's no idea what's going on there. So it's, again, now that you know that there's a line at 5,200 angstroms that rarely, but sometimes does appear in galaxies, you can go and search for it specifically. And again, we did, and we didn't find many more. But we didn't know we should until we did that. So if you do it well, you can start with spectra of galaxies, map them to a 2D space, and then you have these groups. If you look at various areas in that mapping, and objects that are similar tend to group, and then you can study them. But there's really many ways to do it. There's not one way of mapping one data set. And so we're trying to bring this to the people, as I wrote here, and we created a portal where people can play with those data. And Kate Story-Fisher et al. Did something similar with imaging from Hyper Supreme Cam. So this is based on imaging, but the same kind of idea, looking at outliers, trying to solve those to other astronomers. Michelle Lochner and her collaborators did something similar with the code base called Astronomaly. So there's a lot of work happening on those things, and I think they're quite useful tools. I'm going to talk about time series now. I talked about spectra and finding things in spectra, but I told you we're also generating a lot of time series. They're harder. You'd think they're kind of the same because the spectrum is just a 1D thing, and a light curve is also a 1D thing, but they're not the same. And most off-the-shelf algorithms that would perhaps work on spectra would definitely not work on time series. And yet there are, I think, many questions worth answering. One type of such time series, or the most common ones, are light curves. I already showed how many ZTF are generating, and LSST will have even more. They're challenging for various reasons. First of all, they're sparse, and the sampling is uneven. These are two things usually that kill you with many algorithms. They're very noisy, as we said earlier about transients, but also heteroscedastic. Of course, I blocked on heteroscedastic. Fancy word to say that the errors are not the same, so we have different uncertainties per point. Also, it's also difficult to learn the variability when most of your sources are not variable to most detection limits. When they are variable, it's typically periodic, but finding the period is quite expensive computationally and difficult, and there are some experts here in the room. It's not a subject I want to go into. But many interesting sources are not periodic. They're sometimes periodic or quasi-periodic. And we don't have a good way of finding those things. And to put it in the simplest terms possible, here's the light curve of a star. Here's another light curve. Are those two light curves similar? We don't have a good way of answering that. You can't just take chi-square between two light curves. The phases are random, and there's no easy, simple way. How do you interpolate when you don't know what's going on? How many cycles went between your two observations to interpolate between them? So it's a generic problem that I think we should be thinking about. I spent a lot of time thinking about it. I don't have a good answer yet. Hopefully you will. We did try to do the things we can do. So this is an example of a project I did with one of my students with SNIR. We just actually got a referee report, so that paper should probably be online in a couple of weeks. Here we were looking for extraterrestrial technosignatures. So this is radio observations of 600 nearby stars in a few bands, and a huge amount of data, 10 to the 11 spectrograms we had to go through. So we had to do something pretty aggressive to cut that down to something we can handle, and it still took a lot of computing time. The basic idea was that the observations were carried out by observing the star for 5 minutes, then off the star for 5 minutes next to it, then back to the star, off the star, back to the star, etc. Because the main contaminant is RFI, radio frequency interference, human technology. So our main contaminant is also our best guess for what this ET technology would look like, which is a problem. So the only thing we can do is basically trying to find those sets of data. So you can see here the A, B, A, B, A is on star and B, C, D is off star. Find the ones when you're on A, you have something, you go back to it and there's something similar, you go back to something similar, but when you look to the side, there's nothing. This is sort of what you want to find. So by using the correlation between those things, we managed to make it something we can compute. As I wrote, we didn't find ET yet, so I don't have anything exciting to report here, but I don't think that comes as a big surprise. Another project we've been working on is looking at gravitational waves. So again, surprise for me, but it's been 9 years in 2015, I guess soon 10. So it's been a while since we've been measuring gravitational waves from LIGO. And these are time series. They measure the strain at the detector. They measure the as a function of time. So these not light curve, but time series. And the way they've found so far all the mergers were by matched filtering. So you know what it is you're looking for. You're looking for a neutron star merger or neutron star black hole merger. You have these thousands of templates, and you just match them all to your data and see which one sticks. And that's the best way. You can prove that in various ways. It's the best way to find the things you know you should be looking for. No question. But how do you find the things you didn't know you should be looking for? I'm obviously not the first to do it, and they also have a parallel pipeline that tries to do that. But our idea was to try and use unsupervised machine learning to try and learn from the data what is there and try to do it this way. We are not the only one to think about machine learning gravitational waves at the same time, apparently. That list has 400 papers. So these are 400 papers that were written on something that is related to using machine learning for gravitational wave science. But when we started on this, actually we started a bit before, I think we started in 2019, but there are no published ML searches for generic GW bursts, which was what we intended to do and what we tried to do, and we did. Now there are already quite a few. We're not the only ones thinking about this by now. The first thing we did was a semi-supervised search. So what we did there is we used a small sample of glitches. So these are noise transients that appear in the data. We know they're not real. They're very loud, and they have very recognizable shapes. And they were classified by a project called Gravity Spy. And you can see here an example of them. For some of them, we actually know what they are. We know what real-world thing is causing it, but for many, we don't, which is another interesting question. But we use those glitches as a training set. And now we took data from throughout, at the time it was 01 and 02, and classified or basically asked how, given a given spectrogram, does it look like any one of those glitches? And the glitches, you can see here actually how well the glitches separate in this space. And you can see that different glitches do separate really well. And so the hope is that if you have something that's an outlier to the glitch class, so it's not a glitch, there's some detection that is not a glitch, and it happens at both detectors at the same time, then it's potentially something interesting. That was the idea. We searched a lot of the data, a big fraction of the data. We didn't find anything exciting, but that's not too surprising because I think there was one major problem with that approach, is that we trained on high signal-to-noise glitches, but we're looking for low signal-to-noise signals. And that's a problem. But we have a lot of low signal-to-noise background. We have years by now of low signal-to-noise background. And so we've been working on a different approach in which we train actually on the background noise. The idea there, without going into the details, is let's learn the properties of the background when there's nothing happening, which is 99% of the time. So I can just take all the data and learn from that. And then map that into a space. And again, this is actually a true mapping from one of our tests that ended up not so good, but that plot looks pretty well, so pretty good, so I used it. But you can see here how all the spectrograms from Hanford are sort of in this area, and from Livingston are over there. These points I added. I think it's pretty clear. But the idea is you learn to do that, and then again you have outliers to the background in one detector at the same time as you have an outlier to the background in the other, and you call that a detection. That's the idea. We've been spending the last 2 years trying to make it actually work to levels that are, if not competitive, at least presentable. I think we're almost there. The problem is that Matthew here and others are quickly competing with us, and many other people are thinking about this. And I think we're already too late submitting for that thing, right? Yeah. And there are hundreds of submissions. How good are they? Have you looked at it? They're reasonable. Okay. So the field is progressing. That's good. But yeah, this is, I think, a very interesting avenue and relevant in many things. With gravitational waves, we still don't have the results we were expecting, but that's, I guess, part of the game. So there's quite a lot to do, but I think they're really useful tool sets. And I only touched on a few things that we've been thinking about and working on in the past few years. There's also how to deal with integral field spectroscopy, for example, still staying in the optical, or how to deal with multi-model information where you have spectra and imaging and all sorts of features measured, and you somehow want to be able to make inference based on all of that together. For the last part of my talk, I want to talk about the LLMs or chatbots or generative or reasoning models, and I sort of clump them all together. Let's just call them ChatGPT. That's basically what I'm talking about. And I think the revolution is here with a capital R, and I even made it in bold because I think it's a big deal. I use them all the time for pretty much everything, because they're useful, and also because it's sort of my job and I want to see how well they do, and I try them and I sort of push them to the limit. And I get a lot of useful results out of them. I got useful comments on that talk from ChatGPT in multiple iterations. It takes longer to write the question and upload the document than for it. Am I allowed to use different pronouns? I don't know. For it to go through the whole thing and give me thoughtful comments. Not all of them, not always, but some thoughtful comments within seconds on texts and that are very long, etc. So I really think they're extraordinary. Also remarkably stupid sometimes, but they're getting better fast. Especially as a non-native speaker, again, having sort of ability to not have to think about language is nice. There are many common objections. Again, I started thinking about this 2 months ago. I think by now I don't really need to say that anymore, that they're not probabilistic word generators anymore. It's not true. It wasn't very useful as description a while ago, but it really doesn't capture their capabilities today, I think, at all. And it's true that they hallucinate. They do occasionally invent stuff, but they do it less and less. And I think we will just learn to accept it, whether you like it or not. I'm old enough to remember rotary phones and AM/FM radio, and we never had to reboot them. You just picked up the phone and it worked. And there was no rebooting, no plugging, unplugging. And computers came, and they're useful, and they're annoying sometimes, and they sometimes don't work, and we got used to it, and we keep using them, despite the fact that they crash every so often. And so I think we'll keep using LLMs, despite the fact that they hallucinate every so often, because they're useful. It's true that they fail at some really, really silly tasks. Every week, it's something new. I think the last one I saw was their inability to generate a wine glass filled to the brim, because apparently the internet does not contain such an image. The things that humanity discovers today. So yeah, people have managed to go around that, telling you to fill it with red liquid and not wine. But yeah, it's not. Okay, they do fail at weird tests, but they beat human at most tests, at many tests, including Turing. The ones we thought one day will tell us when we have a real artificial intelligence ahead in front of us. Most tests today show that chatbots are better than humans at sounding human. And they're getting better at it. And that's true that it's not intelligence, though I really don't know how we will recognize it when it is. So that's something to think about. And we can and we should move the goalpost as we understand. We're faced with having to understand what intelligence actually means. But that doesn't mean we shouldn't acknowledge the implications of where we are today, which is those things perhaps are not intelligent, but there's something. And so I felt I had to go through that. And I apologize if you don't like it. But I think as products leverage these capabilities, obviously the adoption is bound to soar. And if I'm asking who will reap the benefits of the increased productivity, you can see from real ads that were either found online or this one actually was served directly. So this one I hadn't to go look for it. It was actually served to me as an ad. So basically offering AI replacements to people working. I mentioned for completeness the alternative facts and realities that they will help generate, but I don't want to discuss it, nor do I want to go into the environmental impact. I'll just say that when O3 was it? Yes, O3 came out a couple of months ago. So it didn't exactly come out. They talked about it, but they haven't released it. Every single query cost $1,000 in electricity. Now, people will want the best answer they can get or they can afford, even if it's for a risotto recipe. And so people will burn the planet to get a better recipe. I think this is something we need to think about. And if you don't feel threatened, meet Google AI co-scientists. This is a paper from 2 weeks ago, where they've built a reasoning model built of basically various LLMs that talk to each other and help each other and build an AI scientist. And yeah, it works well. Yeah, there's that. But I want to go back to what's actually our job and just raise, I think, those 3 questions that I feel more entitled to discuss in this context. One is it the end of coding as we know it? Do we need to learn to code? Or should we learn and teach prompt engineering? So writing prompts to chatbots? And how to incentivize our students or kids to learn? And my answer are yes, no, and I don't know. I think coding will just be a thing of the past soon. Well, relatively soon. Just like we don't code in assembly anymore because we don't have to in assembler anymore. We can now talk in natural language and get a better result than when we try to use Python. Glossing over the details, but it's getting there. And so I don't think coding will be a necessary skill moving forward. That's probably a good thing. Should we learn and teach prompt engineering? I don't think so, because I hope at least that this is a temporary thing. Because every new version gets better at understanding the prompts. And usually, at least my experience is I get similar results by just having a conversation. I ask for something, and if it's not exactly what I wanted, I explain why it's not what I wanted. And in this way, after a couple of iterations, we get to where I wanted, instead of crafting these complicated 3-page long directives of what I want and what I don't want, and that sometimes works, sometimes doesn't. At least that's my experience, though I know that companies are already hiring prompt engineers. So this is something that already exists in the industry. And I don't know how we deal with the learning, because we no longer remember phone numbers and we no longer know how to navigate. And soon we won't be driving because we won't need to. And I'm fine with not doing all those things because I don't think I benefit a lot from doing it. But when we get to learning, that becomes a problem, and I don't have a good answer. But I think it's something we should be thinking about. So this was it. I think it's everywhere, and I think it's just the beginning. But it's really happening and has happened at different paces in different places because of needs. I think anomaly detection is one of those things that I've been enjoying using and thinking about, and I think it has many uses in our day and age. But there's still a lot of things to think about on how to do it properly with time series. The latest AI models are powerful and scary, and the societal impacts are already here, and we're not ready. Thank you.
By using prompt engineering, you can just ask the chatbot right now.
Yeah, I mean, that's one way to do it. But again, yeah, it works exactly. I agree. I've never felt the need to spend a lot of time thinking about the prompt. I get it done without it. But while prompt engineering, I think, is not a very important skill, we do need some, call it chatbot literacy or something. But we need to think, just as Google searches were not an obvious thing to do 20 years ago. We need to learn 20, 30, 25, I don't know. We needed to learn how to do that, and how to find the things we're looking for, and how to use those tools. And I think the same thing applies to chatbots. An example I can give is that I taught a class a few years ago at Tel Aviv, a graduate class on supernovae. And I had a hard time thinking about homework problems for the students, because most of the calculations and derivations I mean, there are not many that you can do as a homework problem on that topic. At least not many that I thought were doing. So what instead I gave them was, every couple of weeks, I gave them a paper without the abstract. And the task was to write an abstract and also write like a few sentences what they thought about the paper, which is a skill we, in a way, learn to do. And each one of us within our field, we learn how to read a paper without actually reading every word, how to go to the sections that actually matter, what is important, what isn't, this sort of filtering. I think it's a really useful tool as a scientist, a skill as a scientist, and the students were very happy with it. And I was very proud of myself. And I'm teaching that same class in Stanford in a month. That task doesn't make a lot of sense today. Now, when I have a paper and I want to quickly know what's going on there, first thing to do was to ask ChatGPT what he thinks about it. It won't be 100%, and I can do it better than him for some aspects, and certainly where I'm an expert and he's not, but it is not. But it's everything we've been doing, we can now do faster with those things, and it's a very strange world.
Great talk.
Thank you.
On the time series, we're saying that we don't, we lack a general good metric for distance or similar things like I think we have a good, if we view them all as continuous processes, we know mathematically what the distance is. Particularly if we look that's a sign or any of those, we have metrics. I think the problem is that the time series we're looking at are, as you say, we have signal degradation. And what we don't have is a good way of mapping from that surface into what we're dealing with and knowing what's working. And we're into that regime of finite inflation and we don't know how to tell things well. And that's why we need to do it.
I'm not sure I understood everything you said, but I think the bottom line is the same, which is given two light curves, if I ask you how similar are they, we don't have a good answer.
In the limits of
real data.
Don't have infinite sampling and that's where but that's a data.
Fair enough, yeah.
Rather than an ML problem. I mean,
oh, so your approach is let's get better data? Is that what you're saying? I mean, sure, but yes, but sure, but you can't send everything to space.
No, exactly. But
Nope.
I think it's more of a applied problem rather than a theory. I should finish that one. Yes. Toby, I think about your last question, related slide.
The learning.
So fraction and your figure you think could have been done by
I don't have an answer to that. I have no idea. I don't think they're not at the stage where you can just give them data and they'll write papers. There's a lot there's a lot of work on that now everywhere. I don't know why, by the way, but so many astronomers are trying to build their replacements. I don't understand that, but I guess we work on the things we know and we know how to do science, so we try to teach them to do science. But I don't have a good sense of what I think we'll know soon. I think more and more projects of that sort are being done nowadays, generating hypotheses, testing, and basically building completely automated pipelines from including, by the way, gathering the data. So we'll see where that goes. It's not there yet.
why AI is super dominant in astronomy is because it seems to be good at finding low signal to noise data, whereas we want to discover something, find really high signal to noise results. Is that kind of the main difference?
I don't think so. That's not at least the way I see it. I think again, it's we use complicated tools when we need to. Sometimes we use them because they're cool, but what really drives the community and academia tends to be pretty conservative for good reason. Things change and people accept new tools when they need to, when their worth is, they show their worth. And that's why, with transients, we did it years ago because we had no choice and people saw that it works, so why not? the main reason you don't see that much, but you don't see that much in any other science, is that they're complicated models. And so you don't have a lot of control about many of their aspects. And so it sort of brings it to the sort of black box representation that I don't like, because we use black boxes all the time. And these are not more black boxes than others in some sense. But yeah, I think I don't think astronomy is different in that sense. Thank you very much.